seems to be a force pushing space apart. Dark matter seems to be governed by attractive gravity. Dark energy is governed by repulsive gravity. We don't understand dark matter and dark energy. I'll convince you of that in my talk. I'll convince you that I don't know what I'm talking about. It's just names. But we have an idea what dark matter might be. We think that dark matter might be a new particle species, and we think that dark energy is a manifestation of the fact that empty space, completely empty space by itself, has a weight, that it weighs something. So let me talk about dark matter. What is the evidence for dark matter? Well, this is an image of a galaxy. Very beautiful image, very beautiful galaxy, but this galaxy is spinning, and it's spinning so rapidly that if the only force keeping the galaxy together is the force of gravity from the stars that we see, it's spinning so fast that the stars would be flung apart and the galaxy would not be there. So there must be other types, some other force, some other gravitational force, some other source of matter holding the galaxy together. And observations suggest that if we step back from the galaxy and look at the entire galaxy, including the dark matter, the visible part of the galaxy would just be that yellow disk in the center, and it would be surrounded by a halo of dark matter. We don't see it, but we infer it by the way things are moving. And this halo of dark matter is dense in the center and extends out much farther than the galaxy that we do see. And furthermore, there are other clumps, should be other clumps of dark matter. So if we could see dark matter, galaxies would have a much different appearance. What is this dark matter? Well, there have been ideas over the years that I've worked on some and other people have worked on them. One idea is that Einstein didn't have the last word on gravity, or perhaps Newton didn't have the last word on classical dynamics. This goes by the name of modified Newtonian dynamics, or MOND. Recently, there's been a series of observations that I believe cast this idea in real serious jeopardy. There are some people who still work on it, but they're wrong. Then there's the idea that the dark matter is just normal matter in some sort of form that we don't see. There are different types of planets. We're discovering thousands of planets in our galaxy. There are large gas giants, icy planets, and my favorite type of planet is the rocky planet, named after me, another type of planet. And perhaps there are rocky rogue planets throughout our galaxy, planets that are big chunks of rock just floating around. Or perhaps it's big black holes. These type of objects go by the collective name of massive, compact, halo objects, or machos. Again, observations challenge this idea. There are still a few people who work on this and think this might be the answer, but I don't think this is the answer. I think the most promising idea is that the dark matter is a new type of elementary particle, some type of particle that we have yet to discover that we don't know about. A new type of elementary particle. Well, why can't it be some of the known elementary particles? Our friends, the particle physicists, have been busy for the last 50 years discovering all sorts of particles, quarks, anti-quarks, leptons, anti-leptons, force carriers, and now the Higgs boson. But none of these particles can be the dark matter. What do we know about the dark matter? It must be stable. It has to live at least 13 billion years. So a lot of these particles that have been discovered are unstable. So if we remove them, there's not many left. The dark matter has to be massive because it has to be gravitationally bound to a galaxy. If we remove the massless particles, that removes some of them, and it has to be massive enough, and we don't think that neutrinos are massive enough. No, there's not many left. We also know that the dark matter has to interact with normal matter very weakly, otherwise we would have discovered it. And electrons and up quarks and down quarks interact strongly, so let's get rid of those, and there's nothing left. So if it's an elementary particle, it has to be something that is yet to be discovered. And the dark matter must be a new particle species. So here's a story. Don't look now, but invisible things are passing through you. There is a mysterious, invisible particle species all around us. It's a relic of the first fraction of a second of the universe. And during this lecture, there are a few 100 million of them in this room right now, flying around at about 500,000 miles per hour, and about 1 million of them will pass through you during this lecture. But you can't see them, feel them, smell them, or sense them in any way, and yet they make up most of the mass of the universe. Sounds crazy. So what is the origin of this weakly interacting massive particle species? Well, it's hard to make. We need a large factory to make dark matter. The WIMPs are massive, need a lot of energy to make mass, and they seem to be everywhere in all cosmological structures, so it's logical to think that the idea that the dark matter is a relic of the Big Bang. How were they made? Well, presumably quarks came together in the hot primordial soup, smashed together, and produced WIMPs. Okay, so how do we test this idea? Is it falsifiable? Earlier I said we can use telescopes to look out in space back in time. Can we build a really big telescope and look out in space back in time to when WIMPs were produced by quarks? Yeah, we can't quite do that because today the universe is 13.8 billion years old with a temperature of minus 455 degrees Fahrenheit. When the universe was only 380,000 years old and the temperature was 5,000 degrees, the universe was so hot and dense that we can't see through it. It's opaque. So we can't look out in space back in time earlier than the first 380,000 years after the Bang. We can't look back to 1 billionth of a second AB after the Bang, when the temperature was 1 gazillion degrees, when we think the WIMPs were made. Well, how can we get around that? Well, this is the idea: quarks make WIMPs, but there are quarks inside of protons, normal protons, and maybe if we smash protons together at high enough energy, we can make WIMPs. Perhaps we can reproduce the conditions that were present a billionth of a second after the Bang here in the laboratory on Earth today, and see whether WIMPs are produced. And this is a search that's going on now at an accelerator that straddles the French-Swiss border at CERN, a European laboratory outside of Geneva, Switzerland. It's called the Large Hadron Collider. There they're making primordial soup. That's what they make. Now, we used to make primordial soup at Fermilab, but now we're making it in Europe. Guess we don't have a tariff on primordial soup, so it can be made anywhere. So what are the characteristics of the primordial soup? Okay, no more tariff jokes. What are the characteristics of the primordial soup? 1 nanosecond after the bang, 100 million degrees, it was condensed. In 1 can of primordial soup was a mass corresponding to 50 times the mass of the Earth in matter, 50 times the mass of the Earth in antimatter, and 1 extra mountain of matter, because eventually this matter and antimatter will all annihilate into the radiation we see, and there's a little mountain of matter left over that makes all of the matter that we see. The soup was condensed, the soup was hot. Per serving of primordial soup, there are 4 servings per can. There's the energy equivalent of 10 million years of the total energy output of the sun. It was condensed, it was hot. What are the ingredients of the primordial soup? In every spoonful of the primordial soup are 100% of the daily requirements of all of the elementary particles that we see. But how do we find the dark matter? Well, this is, again, this is one of the experiments at the Large Hadron Collider, just to give you a sense of the scale of it. Here is a person that was left behind in the tunnel. I hope he's okay. And this is sort of the scale of the detectors. So the quarks are in protons, they're scattering, and perhaps they'll make WIMPs, and we'll discover them at the Large Hadron Collider. Now, this picture here, this cartoon I've drawn of quarks